So today we are going to see about the machine learning prediction models in nanofluid modeling for nanofluid flow. So nowadays, actually, machine learning is developed in many domains. It has make many importance in several domains. Not only just mathematics, it is work useful in material sciences as chemical component to predict the enthalpy of a chemical component. Many domains it's worked. It's this particular domain can be fit for all domains. It has a more influential in all domains. Not if suppose if I'm a mathematics, how I will contribute in a biologist. But if I know the machine learning very well, I can contribute it. Recently, I just started my work with one of my friend. He's a biologist in here in Korea. So we are working with this model to found which hormone is a better performance in human body. So that type of analysis we are doing by using a machine learning predictions. Apart from that, we are working in material science also, like how material science adopt this machine learning. For example, the material. Suppose if you are working in the material science, you have a limitation of experiment result. For example, you can apply your heat up to 5,000 Kelvin. For example, it's not more than that, but you want to predict his material strength. For example, it is a 6,000 Kelvin. What is the material strength? So how you will predict? We But by using a machine learning, we can easily predict his material strength. The only thing is that when I was speak with some mathematicians, they says that why you are using a machine learning, you can do the interpolation and you can do the extrapolation. But it's not a correct thing, that because machine learning will predict with this our data. For our data, it will do the training and validation and testing, it will give the result. But if you are working in a numerical scheme like interpolation or extrapolation, we have some data point. In the data point, it will do the prediction. There is a lot of difference between machine learning prediction and our numerical interpolation prediction. So we have to be more clear that why we are using a machine learning. Okay, so how we'll apply this machine learning in our nanofluid modeling? So how I will apply, because we have a numerical data, we have an exact solution, we have a numerical solution, approximated solution, both we have. But why I want to do the machine learning? Okay, suppose you are doing heat transfer analysis or boundary layer flow modeling or blood flow modeling, or you are using channel flow, or you are using a cavity problem, whatever modeling you are working. In this one, you want to know that which parameter is more influential and how it contribute to enhance the heat transfer. Why we are doing boundary layer flow modeling, or why we are doing a CFD modeling, why we are doing channel flow modeling. We have to find a better heat transfer because experimentally not at all everything is possible. So what we do that we are doing theoretically, we say it is useful for experimental. Okay. So for such a cases, what someone raised the thing. May I know any question? Hello, sir. I'm audible. Sir, can you hear me?
Yes, sir, audible.
Hello, tell me, sir. What you want, sir?
Yes, sir. Sir, someone has raised a hand. May I know
Yeah,
why?
yes, sir.
Any
Yes,
any
sir.
question is there? Yeah.
Any question, sir?
Okay. So can I go ahead? Can I go ahead?
You can go ahead, sir. No problem. Later,
Yeah,
afterwards,
yeah.
they will answer, sir.
Sure, sir. Okay, okay.
Sorry, sir.
So why we are doing boundary layer flow modeling, or why we are doing a channel flow modeling, why we are doing a cavity problems? Because we want to find a better heat transfer results. So in the better heat, we have to get more heat transfer. If it is heat transfer is very good, so their heat is eliminated from that place, so we can cool the system, or we can make a more efficient the system. Okay. In such a case, we have several parameters in our study, like magnetic field, we have a radiation, we have a heat source or sink, we have a Darcy number. So in which parameter in our modeling will give an impact in the heat transfer analysis? So if we understand that one, what we can do that when someone doing the experimental analysis, they can tune the parameter. Okay, one question is that how our result will be best for our with the experimental result. So when we are working our nanofluid modeling, we will keep the volume fraction model value is 0.05. So why we are keeping the value is 0.05? Because If your volume fraction value is 0.05, that time only our results will exactly match with the experimental result. That's the beauty nowadays. Machine the volume nanofluid model giving to the fluid dynamics investigation. I think this introduction is enough about the machine learning, why we are going to use. So in this presentation, what we will see that we will see some important modeling in fluid flow problem. Then after, we will see how we'll apply the machine learning. We will take one research paper. In this research paper, I'm going to show you that how to use a machine learning by a simple code by using a Python. And we will see with a manual code and with the package how we do the manual, how the result is coming. If you use the packages, there are several packages are developed. We don't need to spend a lot of time to define or to call. Just the package. You can call the package in Python. You can do it. At the same time, we will do in deep learning also, like we are see in regression and we are going to see in deep learning. In both the things, how we will work on, how we will find a better prediction uh, uh, in the research paper. I will show the research paper and I will show the results. We'll see our results, how it is going to be work. Okay. Hope it will be a good thing. Let's see, go further. So then, before going to start, we have to understand that heat transfer. We know that heat transfer means heat transfer from one place to another place due to the temperature difference. It has been in three mode. One is conduction, convection, radiation. Conduction means the heat transfer from one particle to another particle by the same medium. Convection, heat transfer through another medium like air or fluids. It will transfer through that is a convection. Radiation, it's emitting as an electromagnetic wave. Okay, these are the three basic mode which we are studying, even though we are using in our modeling also. So these are the heat transfer analysis, heat transfer modes of heat transfer. Then what type of laws? There are several laws is there. So the mostly we are going to use the first law of thermodynamics. Thermodynamics states that internal energy of a system is equal to net heat transfer into the system minus work done by the system. So this is first law of thermodynamics, which we are usually use in our governing equation formation and all the things. Then we're going to see about the thermal conductivity. So why we are using nowadays a nanofluid? Because compared to traditional fluids, nanofluid has a better heat transfer performance. How it will be more heat transfer? Because compared to fluid, solid particles have high thermal conductivity. So if we understand about the thermal conductivity, so what type of modeling we are going to do? On the case, we can choose a better material. For example, if we are analyzing blood flow modeling, on the case, if I took any aluminum based material, it will be correct? No, it won't be give a better performance. So that's why if you are working in a biological modeling, the people are going to take gold particles, silver particles, or they are taking copper particles. So high thermal conductive materials they are taking because to deliver the drug in the proper injured pace to cure the thing or enhance the blood flow purpose, they are using this type of materials. So in which case you are going to analyze what is the application of your modeling. Accordingly, we can choose a better material. So for that, already well-defined things is there, but each material already well-defined, but we can understand what is meant by thermal conductivity. Thermal conductivity is that heat energy transport ability of a material. So already well proven that each material have their own thermal conductivity according to the temperature behavior. So actually we are working with the 273 Kelvin to 310 Kelvin, actually our room temperature. For all the cases, the nanoparticle which we are using, it's already well defined. So if we are working in our study, our thermal conductivity is a constant, we will choose the governing equation. So if in our study, we have a thermal conductivity is a constant, we are taking our modeling seems like that. Suppose our thermal conductivity is varying, we will take the variable thermal conductivity. So the thermal conductivity depend on the viscosity. But the main thing is that when a thermal conductivity is varying, we have to consider, for example, if we choose a petroleum purification type of modeling, there the viscosity will change. So when the viscosity will change, based on the thermal conductivity also will change. So when you are going to modeling about the variable viscosity, you should consider variable thermal conductivity. Okay, if you are not considering a variable thermal conductivity, maybe you will not get a proper evidence or proper like experimental occurrence. So you have to choose in a proper way. But many people are discussing without variable viscosity, they are considering variable thermality, but how much it will be occur, we have now any proper evidence. So if your viscosity is varying, the thermal conductivity also vary, so you have to consider with that one. So how thermal conductivity is varying? So if thermal conductivity is a combination of lattices vibration and free electrons. Let us, you have a solid particle. In the solid particle, what we have, that we have a lot of free spaces to uh, transfer the heat from one place to another place. Okay. So on such a cases, give me a while. Yeah. So heat transfer from one place to another place, and there is a lot of free space is available. So in material, it's a strong combination. There they have a lot of free spaces to transfer the energy from one place to another place. But in polymer, you are taking there is a weak bonding. Suppose you are taking a water molecule. In water molecule, the bond is very weak, so it unable to transfer heat. Okay, so there what happened, the bond is going to be break immediately, so the heat unable to transfer the heat. But if the solid is a complete solid material, there is a lot of free space to transfer the heat. That's why metals have high thermal conductivity when compared to polymers and ceramics. Next, we will see basically in our, as of now, in fluid dynamics, we are working in three different cases. First is boundary layer flow, then is channel flow, that's lid driven cavity or square cavity or chamber type of investigation. So before what in fluid flow over a surface is a very fundamental. Initially, it was developed. So how, what is mean that fluid flow over a surface? When fluid contact the surface, form a small thin layer. This is known as a boundary layer. So inside the boundary layer, the velocity variance is high. Away from the boundary layer, it will go as a free stream velocity. So this is a boundary layer analysis. It was initially developed by Louis Prandtl. So what we will analyze the boundary layer, we will analyze the fluid flow, heat transfer, and skin friction things we will be analyzing in this one. So what is the application of fluid flow over a surface case? The main thing is the fluid flow over a surface case is used in aerodynamics, especially for aeronautical things. They are analyzing uh, boundary layer type of investigation, because if we consider the boundary layer, we can classify that this is a laminar, transient, and turbulence. So in turbulence case, in the boundary layer, still the people are working. Many investigation is going on how to enhance a uh, to reduce the drag. If the drag is reduced, we can enhance the efficiency of the material, like um, aircraft material surfaces. So all the things, still investigation is going on. So to analyze the boundary layer has a lot of applications in particularly in aerodynamics. Apart from that, nowadays the people are using for solar energy application purpose, and then the people are using to cooling the electronic chips. Suppose you have a fin, the fin is covered with the fin, you want to cool down the fin. So what they are doing, that they are injecting some cold air or cool fluid with conducting some nanoparticles to chill down the surface. So such a type of investigation is going on, like a microfluidics investigation. So it's based on that fluid flow over a surface case. Then another thing is that fluid flow in a channel. In fluid flow channel, there is fluid flow between two parallel plates. So it will be in this fluid flow case, what we are going to analyze, we are analyzing the pressure drop, velocity profiles, and wall shear stress. For example, a guy have a stenoise, or he have some stenoise. So there you want to like what happened if you have a stenoise, you will get a heart attack. On such a case, the people are taking one drug that it will make cure the heart attack. How it will going to cure? Because when you are taking the drug, that drug contains some nanoparticle. It driven your blood flow fastly to move to tackle such an area. For example, this is our heart pipe. Here we have some stenosis has been formed. So in this one, the blood won't be go properly. If you are using a drug, it will driven the blood flow. We have done one study recently by using a finite difference approximation in blood stenosis artery. What we observed that when we choose nanoparticles, Okay, when we use a gold or silver type of nanoparticle, their fluid velocity is increasing. If fluid velocity increasing means that where the stenosis region will be there, their fluid driven is increasing. If fluid flow is increasing, if the person has stuck or some diseases, he want to be immediate cure. So if he took the material or if he took the drug, immediately the blood is going to be driven, so he can cure with this. He can cure the disease. Okay, he can cure on such a on particular time to make a blood flow or blood pump to whole our organs. So this one type of study we have done recently. So the main application is of fluid flow in a channel is so the biological modeling and pipe flow modeling. If you are working in a pipe in fluid flow in a channel case, it has been used in pipe flow analysis. In recently, we've seen several postdoctoral opportunities in Saudi Arabia because there are a lot of petroleum purification industries are there. There they are calling particularly the guy who more specialization in pipe flow modeling, he getting a better opportunities. So if you are well known in channel flows, especially analyzing a pressure drop, you are familiar with the CAMZOOL or many things, you can get a better opportunity. Or not only teaching, you are getting a industrial opportunity also. So you have to be know what type of modeling, what type of analysis we are going to be do. It will be a better thing to understand. Next, cavity problem. So this my laboratory is computational fluid and computational laboratory. There recently we are focusing on application oriented cavity problems. So if cavity mean that there is a square chamber, the square chamber containing a fluid, it has some heated region, it has a cold region. So due to density differences or buoyancy driven, the heat is transfer from the fluid transfer from one place to another place or heat transfer from one place to another place. There we are analyzing heat transfer behavior, which means how much heat eliminated from the heated region, how much the system going to be cooled. So such a type of analysis we are doing. So you just look at it here. This is a circuit model. So in the circuit model, there are several fins are there, heated fins. Like in our computer, we have a motherboard or we have a circuit modeling. So on such a heating equipment, electronic equipments, how we are going to be cooled more fastly by using a nanoparticle. So how to do the modeling first? So what the researcher they are doing that they take some particular control volume in this region. The control volume is converted as like this. So this is the actual three-dimensional projection. In this three-dimensional projection, the people are considering the square cavity with the heated fin. So heated slits. So if the heated slits is considered, so how much heat transfer is happening into the chamber, how to cool by using a Rayleigh number or if you're using nanoparticles. So this type of analysis, the people are working in the cavity type of modeling. Okay. Not only things that the people are working for solar energy application, like recently the people are what type of research is working is there is a cavity. So here there are one cavity receiver. There are several methods are there to enhance a more efficient solar energy receiver. So the people are initially consider the flat surface. There they did. Now there is another thing is going on. It's called a cavity receiver. In the cavity receiver, there is a disc. It's surrounded like this. So there is a disc. So the sunlight will reflect. Sunlight will placed it here. Here there is a silver foil is containing this. So this silver foil reflecting the sunlight to this receiver. So this receiver containing a square cavity with a nanofluid. So how much heat is gained from the heat and it transferred to the batteries. So this type of investigation recently also is going on in my computation laboratories. So, so cavity type of flow modeling has wide applications. It's completely related to the mechanical engineering. The only thing is that we have to understand what type of investigations we are doing, how much it is important. So how we try to occur with the experimental result. So how we choose the parameter. Suppose if you're working cavity problem, if you're working a natural convection case, the parametric level is 10 to the power 3 to 10 to the power 6. So that is the actual level. So such a type of parametric range we have to understand when we are working a fluid flow modeling. So if you work like that, it will be more beneficial um, to occurrence with the experimental result. So you will get a better um, publication. Now we will come to machine learning. So how to use a machine learning for our problem. So before going to machine learning, we'll see what are the classifications are there. So the first classification in machine learning, we can classify the supervised learning, unsupervised learning, and then the reinforcement modeling. So in this presentation, we are see only a supervised learning. We are not going to touch unsupervised and reinforcement. In supervised learning mean we have some data. That data we are feeding to the system, and we are teaching to the computer that, for example, we have a different type of fruits like apple or banana and mango is there. So you are teaching to the computer, oh, choose the if you are asking show the banana, but how many bananas we have. So it will show, oh, this many bananas are there. So how it will be predict? First, we are feeding the data. We are teaching the computer, oh, this shape is banana shape, and this shape is apple shape. So we are teaching the computer. If you are supervising the computer, it give the result that is supervised learning. Unsupervised mean you are updating the data, but you are not mentioning all the details. Machine itself showing that, oh, this is a banana, this is the apple, like that it will show. That is unsupervised. Reinforcement mean it's quite different from this type of machine learning. It's so advanced machine learning approach. For example, we have a dog. Suppose you have a pet in your home. The pet do some mimic, like it will do some actions. If you like the action, whenever it see you, it do the same action. Like suppose if the pet is jumping, you are feeling happy. Once the pet is understand, whenever it see you, it's going to jump. Okay. If you are not like that, is acting, it won't do again next time. So which means that based on his environmental looking, it change itself his behavior. That's called reinforcement learning. So the reinforcement is a more advanced learning. Still the research is going on in reinforcement investigation. So we will see about how we are working in supervised learning. So in supervised, there are three different categories are there: regression, classification, and deep learning. Regression, we know that linear and polynomial regression, and classification mean you we have a data, we are splitting the data. Like if you are going to e-commerce site, or Flipkart or Amazon, so you want to choose particularly your t-shirt. So what you will do, you're going to sort mean you are classifying. I need L size, I need M size. So that type of you are classifying, then you are choosing your material, you are choosing your product. So that type of classification we will do by using classification. And deep learning means by using a neural network, we are going to predict it, or we are going to find the pattern on recognition. That's called deep learning modeling. So this is coming under the category of supervised learning. Unsupervised and reinforcement is quite different. So before going to machine learning, this is a very basic things that how the mechanism is working. What are the main what are the main things is there? If you understand very well, sorry, you can work a machine learning clearly. First of all, there is a main thing is that cost function. Cost function is an important parameter determine that how will machine learning model performance give a data set. It calculates the difference between expected value and predicted value by single value. Okay, for example, this is our data. Okay, initially we have some regression line. So we are going to calculate the error between actual and predicted line. So once the cost function we are calculating, then we have to update our weight and bias. Okay, by changing to minimizing the cost function, the weight and bias going to be updated. Once your cost function has been minimized, so how much your data will be there, the linear line exactly form nearer to that, so you are getting a better result. So your cost function is reduced, you are getting a better prediction. So it is all one to one. So let us see how it will be work in machine learn. How we'll see with the simple code. Maybe you can very easily understand about what is cost function. So I'm just going to open a Jupyter notebook. Jupyter notebook, it usually used to work on Python. So my screen is visible. I'm just going to
Yes, sir.
open.
Visible, sir. Visible, sir. No problem.
Yes, sir. Yeah, yeah.
Okay, thank you.
No, sir. My Jupyter notebook is visible.
No, sir. Only slide is that cost function like that. That is
One sec. Yeah, one second. So now the notebook is,
yes,
yeah,
visible.
yeah,
Yes.
yeah. We will see how the cost function is working with one simple example. We will choose initially some weight and bias. From the weight and bias, how the data, how the machine learning going to be work. Yeah. So if you are working regression type of modeling, first we have to call for this sklearn. Sklearn is a package is already embedded in Python or Python package. So first we have to call for the package, then we have to work. Okay. So in this one, what we will do that first, we will choose some initial some data like a very simple example. What we can do that, we'll choose some value like x train. We'll choose like a 1, 2, 3, 4. Okay. So this is our future. X10 is our future. Then what is we want to predict? So we want to predict our Y train. So we want to predict our result. We will take like a 5, 8, 10, 12. Okay. So we first we have choose the data, and then what we have to do that, uh, if you are working a linear regression, we need a weight and bias because these are the two important parameters when you are working a machine learning. So we'll choose the weight is initially I will choose for this model I will choose weight is 2, bias is -1. So weight is 2 and bias is -1. So if weight is chosen and bias is chosen, so let's see how it is predicting. So I'm going to print this one. Yeah. For my weight and bias, I got a prediction 1357. But what I have to predict, I need to predict 5, 8, 10, 12. Okay. So this is a linear regression equation. Linear regression equation is what? Weight into x and plus bias. This is the Mm. So this is our parameter for a linear regression. Weight, this is our weight and this is our bias. These are the two parameters. So this is the cost function. Cost function formula is 1 by 2m sum of I is equal to 1 to m h of our parameter minus y actual. This is our actual. This is our prediction. This is our actual. Whole square is our cost function. So our main theme is to minimize the cost function. So initially for our problem, what we got, right? We are getting the prediction is 1357. So then we are going to find a mean square error. So if your cost function is reduced, you are, which means that you choose the better weight and bias. If better weight and bias for the model you chosen, your cost function will reduce, you will get the better prediction. So let us see what is the cost function we got here. So we printed um yeah. So the mean square error is 16, 25, 25, 25 we got. So our cost function is this one. Our mean square error is 22.75. So this mean function we got it. But this is not correct because of our actual value is 5, 8, 10, 12, but we predicted is 1, 3, 5, 7. This is not exactly correct. So if you plot the linear regression line, how it will come? Just look at here. We have a data point here, but we are getting a linear line here. So obviously we won't get a better result because we have a very wide gap between this. So what we have to do that we have to update this curve, which means we have to move this curve to nearer to the data point. If it's moved nearer to the data point, we will get the better result. So how to move? So how to move that? So to move that, what we want to do that, we are calling a gradient descent. Gradient descent is the approach to find a better, which means the best weight and bias for our data. How it will do that? By using a gradient descent machine learning algorithm. So this is our cost function. We know we have seen early. From the cost function, we are going to derivate this cost function with respect to weight and bias. Once it's derivated, we will get the final set of equation. So this equation is called gradient descent equation. Here alpha is the learning rate. Let us see. Initially, it yeah. Initially, uh, when you are going to work a machine learning, it choose somewhere is weight and bias. Okay. So what we want to do that we want to find a global minimum. Once it's find a minimum, so what happened? We are get the better weight and bias. So if the better and weight and bias to change our uh, curve, linear curve to nearer to the data point. Okay. So this is the formula we have going to use to find the gradient descent, which means it is a iterative method. Each time step, it will change a linear curve to reach the data point. So let us see if we apply this formula here. So how the weight and bias has been updated. So initially we have a curve here. Then we are applying alpha is the learning rate. Next slide we will see why learning rate is important. So we choose some learning rate. Then we are going to predict the weight and bias. So initially what we got 1, 3, 5, 7. Initially what is our weight? 1, 3, 5, 7. Now the prediction has been changed 2.7, 5.2 because by using a gradient descent, this is the formula for gradient descent. So we updated weight as well as we update the bias. Now we see that the updated weight and bias. So now let us check. Previously, we got a different mean square error. Now we got a different mean square error. The cost function also reduced. So previously, what is our cost function? We got a cost function is 11.388. So by using gradient descent, we update the weight and bias. Once weight and bias is updated, we reduce our cost function 1.31. So gradient descently we are reduced the our cost function. Our main theme when we are working a machine learning model, we have to reduce the cost function. So the cost function is changed. See, previously the linear curve is somewhere, now it's nearer to our data point. Just look. Previously our blue color curve was what weight and bias we chosen. After applying the gradient descent approach, the curve has been updated here. It's reached nearer to the data point. So again, you change this weight. You are applying this 3.22 as a weight and minus 5.2 is bias. Again, it will be changed. It come nearer to the data point. We will get the better result. So this is how the machine learning will work when you are working the linear regression model. So now we just see that what is learning rate. Learning rate is that suppose we are approaching a minimum, we are approaching a local minimum or global minimum. So in this one, the learning rate parameter is a tuning parameter. It will give a small steps to reach the minimum. If your learning rate will be high, for example, your step is high, what going to happen? Initially, you have a data point here, then it will go here, then it will go. It make a zigzag in our gradient descent approach. So if you choose a minimum gradient descent, it will go very slowly to reach the minimum point. Very slowly it go to the minimum point. If it is high, it will go zigzag to approach the minimum. It will take a huge time. So this also be important parameter, hyper tuning parameter when you are working machine learning. So the tuning parameters, when you are considering, you have to consider maximum 10 to the power minus 3, which means that this level is a maximum level. So this has been analyzed many researchers. They given that the value should be 0.01 to 0.001. So I will choose more gradient. I will choose more learning rate. So I will go step very slowly. Mean what happen? Your data going to be overfit. If it is data with overfit, you won't get a better result. It has some limited value from 0.1 to 0.001. So this is the range of this learning rate. If you are working a machine learning, you have to understand that what is the level of value we are going to choose. So once you get a better curve nearer to your data point, what happened? Your actual weight and the next step weight both are equal and your bias both are equal. So the iteration going to be stopped once your weight is both are equal. Okay. Then the people are facing a very difficult issue when you are working in machine learning is overfitting and underfitting. So if you have to understand that what is overfitting, what is underfitting, so how to avoid these things, it will help you to find a better prediction in your machine learning model. If overfitting, for example, I have a data seems like this. Um, I have a data like this. So if I am applying a linear regression, so it will form like this. So there is a difference between this point to this point. Error is will be high. So by applying a regression is a fine for this type of data set. But what we will do that we will try to capture all points like this by using a polynomial regression. What going to happen? Our machine learning data will capture the point, but it tried to capture all point. If try to capture all point, it's going to good training, but you will get a worst prediction. We have to try to make a linear line if nearer to our data point, not exactly capture all data point. Okay. So if you capture all data point, that is overfitting. So you see here, in this modeling, we are suppose you are using a polynomial regression, it will try to capture the all point. So then your data is the overfit, your result is overfitting. Okay. But here some data point is there, but they form a straight line. But there is a several data points is there is very far away from to the linear line. So this is underfitting. What we have to do that we have to make a best fit line. So that time only we will get the better result. Okay. How we can understand our result is overfitting and underfitting. So when we are performing machine learning, we are splitting our data is testing and validation. In testing and validation, training or validation or training or testing or whatever we can say that. Once that is the way we are going to split our data. So once we split it, so we have to make a error plot. In the error plot, the training and the training and validation will be have a lot of differences. Then we can say that our data is our result is underfitting. Definitely, we won't get a better result. Underfitting means there is a huge gap between validation, testing and training. So this is underfitting, which means that our prediction has a lot of differences from actual value. The good fit mean both will be converge and both will be nearer differences between these two level curves. So on such a case, we can say our data is a good fit. So another way is how we can find it mean accuracy. You have to plot an accuracy. In this accuracy, your training set and testing accuracies be lot of variances, then we can understand your data is overfitting. So this is the way we can understand that first you can perform a model, then you can plot your error. In the error, you can find out, okay, my testing and validation has a lot of variance, so my data is overfitting. My testing and training error is far away, but it's going to be converged, so it is underfitting. Suppose your training and testing validation both are reached in the same converge and both are differences is very small, then we can say, okay, I get a good fit. If your data is a good fit, you will get a better prediction. You are getting a better mean square error and you are getting a better R square. R square is also another matrices to predict the accuracy between the correlation between actual and predicted. It's a coefficient of determinant. It will be give how much our data has been fit. So suppose your problem is overfitting. What you want to do that? You want to reduce the complexity of the model. Like for example, initially you choose your learning rate. There are several hypertuning parameters are there. Um, early stopping, and learning rate. These things are there. So if your your program or your result is going to be overfit, so what you can do that first, you can reduce your uh, learning rate from 0.01 to you can change 0.01. So slightly you can reduce, then you can change complexity of the problem. You can dilute the complexity, then you can avoid the overfitting. If your result is underfitting, which means that you have a lot of variation in your actual and prediction mean, what you want to do that opposite way. You have to enhance your accuracy. You have to enhance hypertuning parameter. Then you will avoid your underfitting. Okay. Okay. There is this only the way is there to avoid the overfitting. No, there is another way is there called regularization. If regularization, what it will do that we will add some penalty term. That penalty term will help to reduce the overfitting or underfitting our data. Okay, there are two different type of regularizations is there. L1 regularization, L1 regularization and L2 regularization. When we have to apply L1 regularization, when we have to apply L2 regularization, that we have to understand. Suppose you have a data sets, different futures. For example, you have a 6 futures or 7 futures is there. In this 6 or 7 futures, only two future you are going to analyze. Only two future you are going to take. Another future you don't bother me. There you can apply L1 regularization. So L1 regularizations mean that the parameter is there, na? Our in our problem weight and biases. So the weight and bias modulus with our hypertuning parameter, the penalty term. If L2 regularization mean the same weight, our parameters, its square, which means that our weight and bias whole square is we are going to use here with our regularization term. All the features are important, but we have to reduce our overfitting mean. There we are going to use our L2 regularization, which means that we have to choose the square of our hyperparameter with penalty term. Through this way, we can understand that okay, we can reduce our overfitting and underfitting. Underfitting, if your result is underfitting, is very easy. You can enhance your complexity of the program. If it is overfitting, is a big problem because you increase your complexity, but you are not getting a better result mean, then you have to use the regularization to control the overfitting. Then you can get a better prediction and better mean square error and better R square. Now we'll see that we'll take this research paper. This research paper initially I was trying to start my initially to work on a machine learning problem. This is they are consider in this problem what they consider that there is um, a circular cylinder. The circular cylinder is in a boundary layer modeling, so fluid flow over a surface. So they are considered several heat and mass transfer investigation, and they find the Nussel number value. So by using Runge-Kutta method, so what they done that the same data with these parameters, they performed artificial neural network. So the same paper we are going to choose, we will work how we will calculate our numerical result with the regression result, and numerical result is our neural network result. Okay. So in linear regression, there is a two classification is there. The first thing is that a simple linear regression and multiple linear regression. So you see in this problem, there are different parameters are there: magnetic field, Smith number, Prandtl number, uh, Casson fluid parameter. There are several parameters are there. In this parameter, you just want to see only one parameter how it is going to be influential. Like suppose you are take a fluid parameter, Casson fluid parameter. In the Casson fluid parameter, how it change the numerical, how it change the heat transfer, or how it change the skin friction. Such investigation you want to do, or such machine learning things you want to do, you want to going to choose a simple linear regression. In this, your future is beta. So in this one, you are going to analyze its regression the same by using first we have to define the cost function, and we have to go for the gradient descent. Once gradient descent in the weight and bias is updated, you are getting the result. But you want to see all your parameters which occur in your system. So you want to find how it will be useful in to predicting the skin friction or to find a Nussel number. So you are going to the multiple linear regression. In the multiple linear regression, how many parameters, how many features you have, so that many weight is going to occur with bias. So here what happened, your weight will be a vector and your features also a vector. So here the cost function defined in the vector form, and as well as the gradient descent defined in the vector form. Once we have to do the training and testing, then we evaluate with the mean square error and R square error. So this is the way if you are working a linear regression with a simple one single parameter or multiple features occur in your system. So how to build a regression? So if we are going to use a regression, there is two way we can do that. The first thing is that we can do a manually, like a gradient descent. We know the formula of gradient descent. We know the formula of gradient descent, so we can type manually our gradient descent. We can use the cost function manually. But if you do a manually, then why the software has been developed? Why the packages has been developed? This is not a correct way to do the scratches, but we can do. But what thing is that we have to tune this one more by if you are doing a manual. So instead of that, you are calling the package which already developed in several Python several language several sources, that it will give a better preference because they are already prescribed. All programs has been like a hyperparameter. Everything has been fixed. We just call the package. We are doing it very simply. We will get a better performance. So first we'll see um, in our Jupyter notebook by using mm, a manual thing. Yeah. So here we have to call for the packages. The first thing is this pandas. If you are using a data, you are going to call the data. On the time we have to use the panda is a library. It's already available in the python. And if you are using numbers, you can call the numpy as a np. Then this, if you are going to plot, so you can use a matplot as a plt. And these are the matrices like a mean square error and r square. So on training and testing, okay, all already exist in sklearn package. So we just call the package and we are going to implement here. Okay. First, what we have to do that we call the pack. First, we have to, when you writing a program, first you want to call the packages, all package. What are the things you are going to use? Then we have to call our data in this in this in this file CSV file. The data which we are going to use for this problem. Yeah. This data I converted into CSV file. This is I treated as my um, uh, futures. So this is my actual. I'm going to predict by using a regression problem. Okay. So just we are just call this by PD the read the CSV. In this one we can call our so first we have to run this one. It's going on. Yeah. So once the package has been run, then it will go for the further step. So first we call the data. This is our data. So here we have all parameters. This is a skin friction they calculated from the numerical result. So once we call this one, then what we have to do that we have to train the model. In this train the model, as we said earlier, what we want to do that we have to split our data for training and testing. Uh, Here what I did that 80% is testing, 20% for training. So if we call the test size is 0.2, which means that 20% we call for a testing and other things we can use for a training. Random state is usually we are calling to split randomly. in sklearn there are different type of random states are there. Even though if you are feeling you can use your any number you can use. Already it was have some prescribed thing to split the data. It will split accordingly. Like if I'm using random state one, it's split in a different way. Initially here 25th in my data 25th value is displayed here 1.8021. If I'm getting random state 2, it shuffle like that. In a different way, it will shuffle. Why we are doing this type of shuffle mean whenever you are run the program, you need to get the same result. If you are not get the same, if you are not classifying the random state, each time based on our predicting the weight and bias, it will choose as a different value, different results it will give. So to avoid that thing, we have to give a same like a shuffle for all the time. So we can use a random state. Any random state you can use. So usually the people are using a 42 random state. So I'm also using the 42 random state. Once it's splitted, we have to call our initial weight and bias. So initially our weight and everything is zero. Initially we can call as a zero because all future weights are zero. Then we have to predict the our weight and bias. How it will be predicted? There is called a closed form solution. From the closed form solution, initially it will predict the weight and bias. So if you want to more about that, you just check sklearn in this site. It will be mentioned that how it will going to predict the um, weight and bias initially. Okay. So here what we did that we calculate manually our cost function. We calculate the gradient descent manually without using the model, without using sklearn model fit regression. Okay. We are doing everything is a manual. Taking the time to work on this. Yeah. So now the cost function, we know the formula of cost function is that what 1 by 2m of sum of uh, prediction actual prediction minus actual. Then that we are going to use our cost function. We know the formula of cost function. So this is the formula for cost function, and this is the formula. This is the formula for gradient descent. From the gradient descent, what going to happen? It going to adjust the our linear curve to fit nearer to our data. So once here what I choose initially my learning rate is 0.01. So we can go up to maximum 0.001 at 10 to the minus 3 level. So iteration, you can choose how many iterations you need. According to your iteration, it take a time to attain a solution. So see how many features we have. We have several features here. We have this many features. So each feature we need to find its weight. So we are find its initial weight. Okay. See here actual value is 1.7472 in this 1.1472. So they predicted 1.176. So what our package has been predicted is 1.1738. So for all values we have predicted like that. Then we can calculate its mean square error. So we got a mean square error 0.0048, and our R square is, which means that our actual and prediction correlation is 0.93, which means nearer to 1%. Then we can make a equation of this. So this is our regression correlation equation. So accordingly we can find for any level of parameters. Now we used for manually we did the gradient descent our cost function. So suppose if you are using this package sklearn without manual cost function with um, uh, manual gradient descent, how we will going to do? Let us see that what we have to do. That first we have to, yeah, you can see the same package we are going to use here, but only thing is that we are going to use we are here after calling the all our packages we have to use our we have to import our data. What we want to do that data is what we are going to use the 1 second. Somewhere is going to typing. Yeah, what we have, we know that to use the table we call pandas. So pandas is a PD panda. Then we need to read the our CSV file we already stored in the site. So our file name is, so this is our file name. Okay, in this file name, I will show the file to you maybe. Yeah. So this is our file we stored into the, like how we are working the latex the same way. So uh, if you're working which folder you are working, so all data should be in the same folder. It will call directly, no need to be store all the time. Okay? How we are working this our latex file the same way. You can look at this. This is the final skin friction. So once we call the thing, we have to mention what is which is our x, which is we want to predict. So if you drop min, we seen that in that one there is several parameter we mentioned in the first column. So we want to drop the first column. We just take we drop the columns. Then that after dropping the whole data we have to take as a x. Our prediction, which is our targeted, that we have take as a y. Then after we are going to train. It's taking time because of lack of internet. Oh, okay, you read dot not read slash CSV. Yeah, yeah, it's reader. Now we have to train our X train, Y train. We have to split our data for testing and training. So through this, what we did a manual code. The same thing we have to do here. Once we have splitted our training and testing, then we have to look at we can look at our data sets. So like what we'll do that we will print our, maybe we print our X train. Maybe you can look at. So we see our X train happen to this. We have to print our training. Okay, it's better we do like this. See, this is our training value. So we'll see our test, how it was splitted. Initially, how it was splitted here, training and testing separately. So like that here, it will split our training as well as our testing. Let me check the testing. Yeah, what it did that. So we'll see clearly. We see our data. In our data, we have from 0 to 32 values, 32 futures or 32 data points are there. In the data point, what it will did that for training purpose, it take 80% of data. For testing purpose, it's take as a 20% of data. And the 20% of data, it choose 31, 15, 26, which means that 36th data point, 26th data point, 27th data point, it chosen. It shuffle by using a random set. If I change the random set is different, the shuffle going to be changed. Yeah. Previously, it's take a 36 as a first, 31 as a first. Now it take a 14 as a first. So it will change the shuffling in different way. Then that what we are going to do that we need to call the model. So what we have to do that here we are doing a manual. We are calling the package. So how to do that in this model? What is there? Linear. Yeah. If you use this linear regression, in this linear regression, in the sklearn, the linear regression package will be there. It call this linear regression package will be called. So this linear regression package will call it do what the programming is exist in the sklearn. Once it's called, what we want to do that we want to fit the model dot fit. So what are the models we want to fit? We want to fit our X train. We want to fit our X train. X train, and we would fit our Y train. Yeah. Yeah. Our linear regression has been called from sklearn, then it's fit with the X train and Y train. Now we'll see our training and testing values. So we got it. Now we look at our R square, for testing R square and training R square. Then we have to, let me check. Yeah. See, in our manual code, we got some different value. In our calling a packages, it's going to change. Here, see, previously we got a mean square error in our in our manual code. We got a mean square error is up to 10 to the power minus 2 level. Here you just look at here. We got 10 to the power minus 5 level actual fit. Our R square is nearer to almost 1. So here it is 0.93. Here it's 0.98 because in the in the calling the packages, they have hyper tuning parameter, they have a regularization, everything. So in that, what it will do, it will reduce overfitting and underfitting. It will give a better result. If you are working in a scratch, what is going to happen? You have to concentrate on all the things. So now the coefficient has been this is our weights for each parameter, each feature. It has a different weights. So this is our bias term. Based on that, we'll make our coefficient equation. Now, okay, we are predicted for this parameter. For first, we have a 1.74, 1.75, 1.5 to 1.5. Okay. Suppose you want to predict, for example, let us take a Prandtl number. Here they use a gas Prandtl number 0.71. When we are working our numerical scheme, we know that the Prandtl number will work for some particular case. If your Prandtl number is 1000, if your Prandtl number is 2000, it won't work. It's very difficult for do the numerical computation. Okay. On such a case, how by using a machine learning, for example, in future, someone has been done with 1000 Prandtl number. some fluid will be there for 1,000 Prandtl number, some fluid will be there for 10,000 Prandtl number. So how you will predict with this data without doing simulation? That we can do with the machine learning. So how we will predict it? You just see here. So what we want to do, that we want to predict our futures. So our future data, we mention as a future data np dot array. So we'll choose initially these parameters, these values. So then after we have to predict we have a model, the model dot predict what we want to predict, the future data. So check. Oh, something's issues happening. Yeah, we missed the comma in between this. Like, so the time is okay, or can I go?
Sir, you
I
can,
have
sir.
to.
No problem,
Yeah,
sir.
yeah.
We are ready to listen. You can, sir. Depend upon you.
Yeah, yeah, okay, sir. Okay. What happened? Oh. Model dot predicted. Some feature is happening. Now let me go with this one. Yeah. So we just take this. Some mistake is happening. Okay. Yeah. See here, for this data set, we are getting the prediction is 1.6607. Let us come here. What data point this one? In this one, you can look at, I think, 1 point, yeah. From the 20th data, here is 1.60985. For actual, what we predicted is 1.064413. Okay. Suppose you want to predict 1,000 Prandtl number. What it will be your result? Here we choose a Prandtl number is 0.72. I just keep as 1,000. Let me check. Yeah. Negatively it going at, which means that the 1,000 Prandtl number, what fluid may be in future, like let us assume it's a crude oil. Maybe let us assume, I don't know accurately, maybe let us assume crude oil. The crude oil Prandtl number is 1,000. If in this modeling they use crude oil as an investigation, instead of heat transfer, it is gaining the heat, which means that the region is so much heat exists into the system, it's not going to cool down. So it's going to negatively your skin friction. So if negatively occur the skin friction, for example, if I choose the maybe like let us take uh, water Prandtl number, what would it be? Suppose the Kessan fluid will be treated as a water. Let us check. Here, slight changes is happening. So accordingly, we can predict our results. Suppose why this is important. If I don't have the program, or if I don't know the what is a Rengekuta method, I'm the mechanical engineer, suppose. But I seen your result, it occur with the experimental. But I want to do your simulation to find a more like a after 10,000 what is going to happen, after Prandtl number is 2,000 what is going to happen. So on such a case, what I can do that I can take your Nuzzle number data from your in your result. That's why many mechanical engineers they says that to mention Nuzzle number skin friction for all parameters. This is the reason. They will take your data, they perform a machine learning, they will calculate. But only thing is that there is a differences between the interpolation and this one. Interpolation, it will be your from your data range, it will predict by using some span interpolation formula, linear interpolation formula, it will predict. But this is not like that. It train your data, it test your data, it validate your data. From the data itself, it will give the answer. So there is a lot of difference between that interpolation and this one. Okay. So that's why if someone will argue, oh, you can do with this or interpolation, why you are doing machine learning? Hi, machine learning is different, and your interpolation is different. Both are in different case. Okay. So only these things. So I hope you can understand that how to do the machine learning by using a linear regression with your own scratch code, and you can use by calling a package. Now let us go how to use um, like a neural network. The same thing, how we will apply a neural network. So what is a neural network? Neural network is a quite different concept from the regression. Regression, you have a weight and bias. It update the weight and bias. It will get the solution by using a linear or polynomial regression or whatever it may be. But if you come to the neural network, it's quite different. That here there is another new thing will be there called activation function. So the activation function will play a role to transfer your information from one neuron to another neuron. Sorry, in neural network, what it will be there, right? So you have an input layer. In between, you have hidden layers. So the hidden input layer, you are feeding your data, your informations. That information transfer to the uh, another layer. How it will transfer? How it will transfer? By using activation function, it transfer the information to the neighbor neuron. In our human brain, we have electrochemical process, the biological processes. If you have if you have anger, that one different type of electrochemical chemical will be formed. If you are happy, the dopamine will form. So this will transfer to show your whole body to enjoyment or to sad or to anger, whatever it may be. That electrochemical process will be there in the human body. How it will be work in neural network? That neural network, the electrochemical process is called activation function. It transfer your information from the neuron to another neuron. It will transfer, then finally it come to the output layer. So if you take one particular neuron here, it seems like this. So here you have activation function, your weight and biases. It will from that activation function. There are different types of activation functions are there. So they call a sigmoid activation function, ReLU activation function. Each activation function has a different formula. Let us go with the sigmoid activation function. If it's sigmoid activation function, e to the power z minus x plus bias. Here z is indicating this one. Okay, so it will be called this here. So it will find the exponentially, then it will find the solution. So each activation function have a different types of set of equations. So there we are feeding our data, it will get the solution. So how to do the neural network? The neural network is simple, but if you are working a neural network, you need to call this package called TensorFlow. The TensorFlow was developed by Google. It is over a long period. The people are working in TensorFlow. If you are familiar with the TensorFlow, you can work in any type of machine learning model or any type of deep learning neural network models. So there are different things are there. PyTorch is there now. Deep XPD development is going on, but initial stages are TensorFlow. So we have to call this packet TensorFlow as similar what we done the earlier. So we have a training and testing. So we have to split our training and test, and we call a random state. Then we need to call a neural net. We have to design the neural network architecture. So this is our input layer. Then this is our hidden layer. This is our output layer. So we called here a ReLU activation function. So activation function means, for example, how it will be work. This is here. If it's sigmoid activation function, it will be go like this. So here we have a threshold value. So from the threshold value, it will split as a yes or no. For example, if you are have some data, you have some medical data. In the medical data, um, um, the medicine or company or whatever maybe, it will giving a split me which guy has been diabetic, which guy has non-diabetic. On such a case, if you are working in neural network, what you want to do that you want to use a sigmoid activation function to do the classification. So our e-commerce sites also, it will be work like by using a sigmoid activation function. If you are affected with diabetic, your value is 1. If you are non-affected, your value is 0. So if you are nearer to diabetic, it is 0.45 mean. That time also it will show that you are non-diabetic. If you are 0.51 also, it shows as a you are a diabetic or initially diabetic. So if you want to classify like this, you can use a sigma activation function. So there are different types of activation functions are there. So you just go through on when you are working a neural network problem. Okay. So then first you have to call the TensorFlow, then you have to train, then you have to have a neural network. You are did the activate your architecture. Okay. If our linear regression, what we did that we use a gradient descent to minimize our cost function. So how you to do in neural network mean we need to call as a optimizer. So there are different types of optimizers are there. Usually people are using a Adams optimizer. In the Adams optimizer, work with the gradient descent approach with some advanced approach. So if you want to think, if you want to know about this, you just Google it. You will get more information about the Adam optimizer. So the work how what it will work. I mean, you can understand the comparatively what is the difference between a deep regression and neural network. Okay, in regression we will do like a gradient descent. Here the same gradient descent will be advanced. It's called optimizer. So once the optimizer has been called for, so our learning rate also we have a learning rate. So then we have to fit our model. Approach mean there we called a iteration. Here we called a approach. And the thing next thing is a batch size. Why we call the batch size? These things are all we know that hyper tuning parameter, which means to tune the architecture for the better performance. If by batch size means suppose you have a 20 data. So 20 data, the same time you are going to do the computation, you are splitting as a different batches. So 10 batch is one, another 10 batch is two. Both batchly it will enter into the computation, which means it will be helpful to find a better result. Then varboss is nothing but when you are doing computation, it will show all informations in the step size. So that's varboss. If varboss is kept as 0, you won't get information. If varboss is 2, up to 0, 1, 2. If varboss is 1, it will give one set of information. If varboss is 2, it will give another set of information. This is the varboss is not that much important. It's just for our you want to check our update, that one only. So once we fit, we call architecture, we fit the optimizer, then we are going to tune. As usually, we are calling our mean square error, we are going to predict. So this is the way of to find the neural network. Let us see the same problem by using a simple feed forward neural network, how it will going to work. So same way, here we call the package TensorFlow instead of to calling sklearn. But to matrices also we have a mean square and R square. Okay, so what we'll do that. So uh, we call this one here. We yeah. So first we have to run this, then yeah. If you are working in TensorFlow, it will take a little time because it's a huge packages occur in Python. It will take a huge time to understand that one. Yeah, we call the data set. Then again, we are doing the same thing. We are splitted. Here I given 1993. So it's not a matter that the random set what you want to use. Okay, it's up to you. You can use anything. Maybe you can use your birth year also. It doesn't mean that. Here learning rate I kept as 0.01. So we said already it's up to 0.001. So you can in between you can do the adjustment for to avoid the overfitting and underfitting. So we call the architecture. This is our neural network architecture. I kept as only one hidden layer. If you want, you can add more hidden layer. If you are working simple data, this architecture is fine. But if you are working large industrial data, you have a large medical data. On such a case, you can enhance your hidden layers more. So once we done, we call the Atom optimizer. So we are going to, yeah, the iteration is started. So in if varboss I kept as 0, so we are getting a loss function and value of loss in each time step. So if you off it, you just get up to the time steps, how much time steps happening. That only the thing is difference. We'll wait up to it's running. I think it was yeah, the iteration has been done. So let us see. Here we have not tuned much. So we are getting a huge variation in our mean square error and R square error. Because this is very simple feed forward neural network. You can use any neural network. Like nowadays, the people are using convolutional neural network. It's a very strong neural network to predict the pattern of image processing. In all cases, development is going on in convolutional neural network. So you can use a convolutional neural network. You can enhance your architecture. You can use your more hyper tuning parameter. You will get a better result. But whatever approach you are going to use, main idea is this one: cost function, gradient descent, mean square error, r square, accurate. Something will be different. So main thing is this one only. So let us see that because um, we have not a proper r square, it is be very small, 0.0.8. So that's why we are getting a lot of variation in our actual and prediction. Now, so let us see one more profile I will going to show you. Maybe you can understand that. Let's see this profile. See here, as we said earlier that um, like yeah, when we can understand that the data is overfitting or underfitting. Okay, our training and testing result will be variation is high. Maybe I will use a different color. Yeah, our training and testing difference is high, then this is a overfitting. Small variation will be there that we can call underfitting. But here what happened? We have very tiny difference here. So once the approach is increasing, it's going to converge, but small variation will be there. This is also good fit, but due to the hyper tuning parameter, it's not give a better result. That's only the difference. Okay, if you enhance your hyper tuning, maybe it will be changed. Maybe for this, let me try one time. The hyper tuning parameter is 0.01. Maybe what it going to be happen. Variation is going on. Yeah. Now some yeah, now you can see that I I reduce the learning rate. Initially, we kept the learning rate is um, initially we kept the learning rate is 0.001. I reduce the learning rate because we have very small data set. For the learning rate, if you're going to too much also, it's going to nearer to the overfitting type of things. Okay. Or nearer to overfitting, not exactly overfitting, nearer to overfitting. But I reduce the learning rate. So due to the reduction, what happened? We are getting a better R square, or we are getting a mean square error very uh, um, near a very small mean square error. So from this, we are getting actual and prediction. Um, uh, Actual and the prediction almost nearer to this. Okay. Mm, this is the way. Uh, so error also it's almost similar. It's going to reduce due to changing the hypertuning parameter. Now everything is through this. You can work in the machine learning problem to predict your Nussel number. Thank you.
Sir, thank you, sir. Thank you for your
Yes, sir.
valuable speech and very
Yes,
informative
sir.
and nice session, sir. All the participants very much happy, sir.
Thank you, sir. Thank you, sir.
Okay, sir.
Um,
Dear participants, please fill the feedback form and the certificates will be provided soon. I will get ready. And one thing is that in the WhatsApp group, I have mentioned that some list with your serial number and the ID is provided in the certificate. Your serial number is your ID. Please look it and I will send. If anyone have don't have their name, please send to me. I will send again. No problem. Please don't post repeated messages. Thank you. Anyway, thank you, sir. And finally,
Thank you,
coming to
sir.
vote of thanks. I am so much happy to organize this such a wonderful international faculty development program. First of all, I thank my management for allowing me to organize this program and my staff for complete support for initiation to till end of the program. I should convey my sincere thanks to my beloved senior Dr. CSK Raju, Hayang University Postdoctoral Fellowship, completely for sincere support in this FDP. Also to all my advisor committee members, my guide SVK Verma sir and my seniors Durga Prasad, VIT Chennai, and all this one end. And coming to another end, I have two main roles. That is, one is resource persons, the from day 1 to day 5. The first day Shivraju sir and day to Bagali sir and Mallikarjun sir and our today's session sir. All are very thanks. And the participants are the key role to this grand success. Without these two, nothing can be done. Hence, I thank to each everyone. With all of this, I end this program. Please don't forget to fill out the feedback form and don't worry about certificates. These will be posted soon in the WhatsApp group. If anyone don't have their name, please ask me. I will send it. Thank you. Thank you, sir.
Thank you, sir. Yeah, thank you.